Before we start on this massive stoichiometry worksheet, I want to emphasize that I utilize the roadmap approach to teaching and conceptualizing stoichiometry problems. It's revealed in its full glory here, and I think that this demonstrates the true effectiveness of the roadmap. First of all, demonstrating the centrality of the mole concept, the fundamental definition of the mole, the relationship to the number of particles, and then possibly most importantly, the way in which you can determine the number of moles and relate the number of moles to macroscopic measurements, whether it be a pure substance with the mass, whether it be a solution with the volume, or whether it be a gas given the pressure, volume, and temperature of the gas. So this is how I will be solving all of these problems. If you don't understand the roadmap, if your teacher insists that you use some other method, so be it. But I really do feel after dozens of years of teaching it this way to tens of thousands of students that this is the most effective way to think about stoichiometry, the mole, the grams, balancing equations, and so on. So we'll start off simply with the definition of the mole. This first question, very much a holistic question about it. First of all, is a mole 6.02 times 10 to the 23? Absolutely, that's exactly what it is. A pair is 2, a dozen is 12. A mole is 6.02 times 10 to the 23. Why such a silly number? Because 1 mole of particles of a pure substance weighs the same as the relative mass in grams. Thus, the mass of 1 mole, the molar mass of a pure substance, is the relative mass in grams. Totally. 1 mole of oxygen gas, O2, weighs 32 grams. Well, O is 16, 2 O's is 32. That is the relative mass of O2. Thus, 1 mole weighs 32 grams. The molar mass of O2 is 32 grams. Now, 1 mole of oxygen gas contains 6.02 times 10 to the 23. So there is indeed the mole. Oxygen molecules. Yes, because when we have oxygen gas, it's O2. That is a diatomic molecule that contains 2 oxygen atoms. So that's good. 1 mole of oxygen gas contains 6.02 times 10 to the 23 oxygen atoms. No, because the gas is not oxygen atoms. The gas that we measure out, the gas that we observed, is a molecule containing 2 oxygen atoms. Thus, 1 mole of oxygen gas would actually contain 2 times 6.02 times 10 to the 23 oxygen atoms. So therefore, E is the correct answer because that is the false statement. Next couple of questions might seem to be a little bit trivial, but it's really important to emphasize that you cannot work with stoichiometry if you haven't got the right formulas of compounds. And rubidium carbonate is an excellent one to illustrate this. First of all, rubidium, find it on the periodic table. It's an alkali metal. It has atomic number 37, atomic mass 85.468. We'll probably call that 85.5. Now, the important thing is that as it is an alkali metal, when it makes compounds, it is going to be Rb+, cations that have lost 1 electron from the rubidium atom. Carbonate, you've just got to know, is CO3 2-. Thus, rubidium carbonate is not just RbCO3, as the unsuspecting student will say, but you have to have 2 of the rubidiums to match up with the 2- charge of the carbonate. So rubidium carbonate Rb2CO3, and that's the big point of this. Got to get the right formula, because then when we get the molar mass, it's not just going to be 1 of the rubidiums at 85.5, it's going to be 2 of them to go with the 12 for the carbon and then the 3/16 for the oxygen. So the molar mass of rubidium carbonate, add all that up, 231 grams per mole. Similar situation here, except we're going to take a little bit further. Number of moles in 35.6 grams of magnesium hydroxide. So let's look at our roadmap. We see that we're dealing with magnesium hydroxide and it's MgOH2. If you just say MgOH, you're going to get a wrong molar mass, and if you get a wrong molar mass, you'll get the question wrong. So anyway, we've got MgOH2, magnesium hydroxide is our question. We're told 35.6 grams, so we're given the number of grams, and we're asked for the number of moles, which will be down here. So therefore, all we have to do is go from grams to moles. That is our step 1, and indeed our only step. So we'll pull out that part of the roadmap. Let's see what we're doing here. Grams to moles. Grams is moles times molar mass, so that's going to be the relationship we use first. We know the grams is 35.6 grams. Moles is what we know. Molar mass here, well, of course, it's magnesium 2 plus, hydroxide 1 minus, so therefore magnesium hydroxide, as we've already said, MgOH2. Molar mass of that, therefore, magnesium 24.3, oxygen 16, hydrogen 1. We've got 2 of those, so 2 times that. So punch all that in your calculator, and we determine that we have 0.610 moles of magnesium hydroxide. Taking it a little bit further now, calculate the mass in grams of 1.67 times 10 to the 23 molecules of CBr4. Well, here's our wonderful roadmap. We're dealing with CBr4, so we'll say that that's substance A. What do we know? Well, we know how many molecules there are, so that's the number of particles, and we're asked for the mass in grams, so that's going to be there. So now this is a two-step question. We first of all, in step 1, have to go from particles to moles, and in step 2, we have to go from moles to grams. Pull out the important part of the roadmap. Step number 1, we've got to go from particles to moles. The relationship we'll use is that particles is moles times 6.02 times 10 to the 23. The particles here, well, it's CBr3, which exists as molecules. So we have 1.67 times 10 to the 23 molecules. That's going to be the number of particles there. Is the moles times 6.02 times 10 to the 23. So we have 0.277 moles. Just divide 1.67 times 10 to the 23 by 6.02 times 10 to the 23, and we get 0.277 moles. So we are this box here, the number of moles, 0.277. Step 2, we now go from moles to grams, so we use that same relationship we used in the previous question. Grams is moles times molar mass. In this case, though, we're asked for the grams. Moles is 0.277. Molar mass is going to be C, which is 12. Br, which is 80 times 4, so punch all that in your calculator, and we get 92.0 grams of CBr4. Question 5, number of atoms in 14 grams of nitrogen gas is the same as the number of atoms in all of these different masses of magnesium. Well, that's our roadmap here. We're given the mass of N2, and we're effectively asked for something particulate, something submicroscopic, the number of atoms. So therefore, the first thing we've got to do is get down to this stage. So step 1, grams to moles. Step 2, moles to particles. So pulling that out, step number 1, we've got our grams. We're going to go from that to moles using the relationship grams is moles times molar mass. Throw everything in. 14 grams is N times. Now nitrogen gas is N2. So it's 2 times 14. So in other words, we have half a mole of nitrogen gas of N2. So now step 2. We know how many moles we got. We've got to go to number of particles. So big N, little n times 6.02 times 10 to the 23. Throw in the 0.5 moles, and we get that big N is 3.01 times 10 to the 23 particles. Particles are what? Well, it's particles of nitrogen gas, and nitrogen gas is N2. So therefore, the particles are molecules of N2. So we have 3.01 times 10 to the 23 molecules of N2. However, the question dealt with atoms. Well, how do we go from molecules to atoms? Well, we see that there are 2 atoms in one N2, 2 nitrogen atoms in one N2. So therefore, the number of atoms is actually 2 times 3.01 times 10 to the 23, which is 6.02 times 10 to the 23 atoms of N2. So we got number of atoms is 14.0 grams of nitrogen gas. Number of atoms in 14.0 grams of N2 is 6.02 times 10 to the 23 atoms. And of course, that is 1 mole. 6.02 times 10 to the 23, 1 mole of nitrogen atoms. So therefore, we want 1 mole of magnesium atoms. Well, what does magnesium weigh? 24.3. So 8.1 grams, that's not a mole. 18 grams, not a mole. 9 grams, not a mole. 24.3 grams of magnesium. is a mole. So just take it through because it was kind of a longish type problem. Number of atoms in 14 grams of nitrogen gas, well, we found that's 1 mole of atoms is the same as the number of atoms in 1 mole of magnesium, and 1 mole of magnesium weighs 24.3 grams. Calculate number of oxygen atoms in 29.34 grams of sodium sulfate, Na2SO4. Again, this is a question that emphasizes that particles are not necessarily just atoms. Indeed, particles are very rarely atoms. But anyway, I leap ahead. I get ahead of myself. See what we're looking at here with the roadmap. We're told that we're dealing with sodium sulfate to start with. We give a number of grams of sodium sulfate, so that is our starting point. And we're asked ultimately for particles, for oxygen atoms, which is something submicroscopic and particle-wise. So therefore, we're obviously going to end up with particles of Na2SO4. So step 1, grams to moles. Step 2, moles to particles. Pull out the salient bits. First step, going from grams to moles, done that many times now. Note grams, 29.34 grams, moles, molar mass of sodium sulfate, 2 times 23, plus 32 for the sulfur, plus 4/16 for the oxygens. I'm not going to dwell upon molar masses after probably the next question. I'll assume that by this stage you're really, really good at them. But anyway, punch that in, we have 0.207 moles here of sodium sulfate. Now, step 2 is, of course, we use the particles, is moles times 6.02 times 10 to the 23. Throw in the moles, 0.207, and that gives us 1.25 times 10 to the 23 particles. Now, that's particles of what? Well, the whole calculation has been based upon Na2SO4. So that's particles of Na2SO4, which I'll call molecules, even though, of course, as it's an ionic compound, they're not molecules, but formulas, however you want to say it. Now, of course, the question itself was number of oxygen atoms. Well, how do oxygen atoms play into this? There are 4 oxygen atoms in 1 Na2SO4. So if we have 1.25 times 10 to the 23 Na2SO4s, multiply that by 4 to give us 5 times 10 to the 23 oxygen atoms. As our last question in this particular section, 0.1 mole sample of ethene, C2H4 contains how many atoms? Well, this is again a sneaky one that under exam conditions people don't do the extra step. Okay, we're dealing with ethene and we're asked about atoms. Well, of course, ethene exists as molecules. But again, I get ahead of myself as we plan. Here's the roadmap. We're told about C2H4. We're given the number of moles, so this is our starting point. And we're asked atoms. Well, that's particulate, that's submicroscopic, so it's going to be something to do with this right here. So only one step as far as the roadmap is concerned. Pull out this particular part. We got the moles. We go to particles using the relationship. Particles is moles times 6.02 times 10 to the 23. We got 0.1 moles, and so therefore we have 6.02 times 10 to the 22 molecules of C2H4, because that's what we were calculating. Well, we wanted atoms. How do atoms relate to molecules? Well, there's 2 carbon atoms and 4 hydrogen atoms in 1 molecule. In other words, a total of 6 atoms, 2 carbons and 4 hydrogens. So therefore, the number of atoms in this much ethene, 6 times 6.02 times 10 to the 22, which is 3.61 times 10 to the 23 atoms. So this first little section dealt with essentially that little triangle at the top left of the roadmap, the relationship between grams, moles, and particles. Very important you have that fundamental relationship down. We can take a pure substance, we can weigh it up, and by using the concept of moles, we can determine how many molecules, how many particles of the substance there are in that particular mass.